Thanks, Bartlomiej, for letting me know I'm not live. It seems I am live now. This is good. Cool. So, if you have any comments, if you have any comments, please be sure to post them. They'll come up here all the time. And when they come up, I can see them. I might want to reduce the windows so that the comments are always there. And we can everyone can see what they're chatting. Ooh, thanks. Yeah, you guys can see how bad I am at typing now. Cool. Should we live now? Okay, so what we wanted to do today is explore power management on in Zephyr with Nordic NRF54L, which is this. I can show you the actual board itself. Here's the actual board, which is this actual board. Yeah. Oh, nice. It's got a little schematic or a little legend on the back, which is pretty cool. I hadn't looked at that yet. Shows you how prepared I am on this. Okay, cool. So today what we want to do is explore power management on this Nordic NRF54. And the way we're going to do that is by attempting to implement a low power, does this have a battery? I thought the 54DK had a battery, or maybe that is maybe that's the 52DK. Is it the 52DK that has a battery, CR2032 battery holder or something? I thought this one had one as well, but I hadn't noticed it didn't have one as well. But that's not a problem. What we really want to do today is make this thing run a temperature sensor on low power. And this might be quite a long stream, because what I'm going to do here is I'm going to dig down into the system itself. I might have to read a couple of documentation articles to find out about it. The thing I know is we did try this with a 52840 a few months ago, maybe last year with Bartlomiej, and I think we also stopped because we couldn't manage to run the battery management system, but that was in a rush, and we weren't exactly where we are now. So what we're going to do today is find out about this device, the power management device. Then after we find out about the power management device and how to use it, we're going to see if we can use it within Zephyr. I'm trying to avoid using the Nordic Connect SDK. I don't know why, but I'm trying to avoid using that for a while. So the first thing we're going to do is jump into documentation, see how we can use the NRF power SDK or device. There is one. Here it is. It exists in Zephyr. Another thing I found is that it is enabled on the 54H peripherals. Actually, no. This is Nordic Common. So it's enabled in the common peripherals, which is cool because that's where I think NRF power is in here. NRF power. Yeah, so it's here. If DT has compat in Nordic NRF power, then config has power. So let's actually, the first thing we're going to do is let's check that compat. Let's check the DT for that, the device tree for the built one. Let me know if you can hear me. Let me know if you can't hear me. Let me know if you have any questions. So let's cut build Zephyr.dts. Zephyr.dts. And then here we're gonna do grep. I think we're gonna do grep something like NRF power, something like that. Power, let's just do that. Power, low power enabled, compatible power, Nordic NRF power. So cool, NRF power, NRF power, and then I'm gonna do dash b d5 and maybe a 820, so we can see the whole thing. NRF power, where is it? Okay. Here it is. So that node power SOC peripheral blah 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 GPR. So that's 1 2 3 4 5 6 7. Okay, so let's do so it is there, the status is disabled, and yeah, okay, cool. So the status is disabled, so we need to sort of enable this thing. But when we enable this thing, what changes? I wonder if anything changes when we enable this thing. Let's actually do that. And shall I make my code window smaller so that I can actually see when you guys talk as well? Let's actually do that. Yeah, Nathan, I think your comment got lost. What's your comment, please, Nathan? Hi, Nathan. Welcome to the session. I think your comment got lost. Let me know what your question is. It's kind of distracting having this here because I have to like come on, don't do that. I don't want that. I would like not to. Okay, yeah, bear with me. I'm just resizing my screen so that I can see. Hi, Nathan. Yeah, nice. No, that's an important comment. Amazing. So let's actually just change this this thing. Let's actually just change this this app, the Blinky app. So samples basic Blinky, which is the one we're running around. I wonder if this is the build folder. No, this is not the build folder. So Blinky, and in here I'm just gonna ignore everything and I'm just gonna go app.overlay. I'm not making a new app because we are doing kind of like exploring and I don't want to bother making a new app. We might make a branch and we might push up a branch if this becomes something. We'll see. Okay, so let's, in the app.overlay, let's do and power. What do we want to do? Which one do we want to manage? Power management. So you see, add power, this one, we want to enable it. It's disabled. Bartlomiej, do you see that? It's disabled. So I'm gonna try and enable it and see what happens. And power, and I think your status equals okay. So let's do that. Let's do that, and I think that should be okay. It should be able to build now. Okay, let's do a build and see what happens. If it will did I change the right file? Basic Blinky app.overlay. Yeah. Dash P. Just flash. I think we should have some logs somewhere here. Yeah, it's booting, it's on, it's off, it's on, it's off. Okay, cool. So the other thing we want to do is cut build NRF power. So 810 probably. Cool, status is okay. So we did enable it. want to do is we want to do let's look at power management in Zephyr. Let's see, is there any shell stuff? I want to see shell stuff. I want to see shell stuff. I want to know if power has any shells, if there is a power shell. Oh, I can actually just search it. Let's leave that there. Okay, config search. This would be quite easy on like an STM32 or something, or something that doesn't have its own power subsystem. So with Nordic, it's kind of new because I mean it's kind of strange, huh? With Nordic, it's kind of strange because they have their own proprietary power system, and we need to kind of know how that power system works. And Nordic does this thing where they make their own software, and then they share what they want with Zephyr, and then most of the other software is in NCS, which is Nordic Connect SDK. Most of the other stuff is in here. I have no problem using this. I haven't learned how to use it. I don't know how to use it, so I've avoided it for quite a while. And I actually like using Zephyr. I like using plain Zephyr so I can jump between devices as much as possible. This comes from someone who works at a place where we have our own custom Zephyr SDK and whatever. So I just like using the vanilla Zephyr, and then also it makes the streams a lot more shareable because a lot more people can use it. Power. So power, there's a lot. So there's a lot of power. Is there something like a power shell? So there's no power shell. Okay. How can can we do something like, let's just go back to the documentation of power and see if we can we do shell commands here. Ooh, yeah, we can do something like that. So let's actually PM device shell. So there's a PM device shell. But this will need config PM device, and I don't think we can use config PM device because Nordic will not allow us to do it, if I'm not wrong. If I am not wrong, Nordic will not allow us to do that. I think that was the experience that we had last time. So let's do here. Let's actually do config shell equals yes. Config shell equals yes. So first of all, let's actually just see if we can build that. We might have to make the overlay. We might have to actually make the overlay happy by providing a UART, but let's see. I'm assuming a UART might be already provided by the other overlay. So I think it's fine. Let's see. Let's go here. There's a 1, there's a 2, there's a 1, there's a 2, there's a 1, there's a 2. Okay. So let's go back and remove this print here. Just keep the log, just keep that, and then we can build again. The reason I'm removing that is so that we can actually remain with the shell and use it. We know the LED is working because the LED is blinking off and on right in front of him, and that's that's helpful. Okay, cool. So that's coming along. So I don't know if I can do PM device, but let's actually see what happens here. Yeah, so this should be good, and then we can do a clear. I like that. Device list. So there's a clock, there's a GPIO, there's a GPIO, there's a GPIO, all the GPIOs are ready, UART is ready, and that is it. I don't see power, so let's try and actually define let's try and actually follow this. So device power management, let's actually just try and show this. So there's two kinds of, Bartlomiej has had this before, so I don't know why he wants to hear this again. There's two kinds, we've done this whole thing before. So there's device power management, and this works on the whole device as a whole. Basically, what this does is that it manages the power of the device as a unit. So if it shuts down the device, if it goes into power saving mode, everything goes down. So let me know if you can actually read this. Device power management in Zephyr is a feature which presents mechanisms to coherently affect the control of power management actions to be taken by device drivers. This control is based on unambiguous expectations, which could be set by any component of the system, and on power-related dependencies that devices may have on each other. So, if a temperature sensor needs a clock, it can say that it needs a clock and the clock shouldn't go off, something like that. If your video device needs I2C, it can say that I2C should not be taken off because it's using I2C, and I2C should not be taken off. That's all. That's basically what that sentence is. And this is kind of what the API in Zephyr is trying to enable us to do, so that we can control the powering of the device all the way from the actual peripheral or the actual device that we're using in the end. Cool. So there's two kinds of power management in Zephyr. There's device runtime power management, which is kind of the new one, and then there's system managed device power management. Device runtime power management involves coordinated interactions between device drivers and subsystems and applications. While device drivers play a crucial role in directly controlling the state of devices, the decision to suspend or resume a device can also be influenced by higher layers of the software stack. Basically, what this means is you can have like let's say you have like a temperature sensor, and you have a temperature sensor, and it has it implements power management callbacks. You'll see them. We'll walk through them. Today might be actually a long stream because I intend to like kind of walk through this thing from beginning to the end. I'm not going to explain too much. Whatever I need to explain, I'll explain. I'm not going to start from blank and whatever. So basically what you need to do is you need to enable your temperature sensor driver to be able to go into power savings or suspend or whatever. And what I just read, while device drivers play a crucial role in directing the controlling of the device drivers play a crucial role in directly controlling the power state of devices, the decision to suspend or resume a device can also be influenced by higher levels of the software stack. Basically here, a device can say, I want to go off because I'm not doing anything, but a subsystem that is above the device. So Zephyr is like Zephyr, kernel, subsystems, and then devices. So a subsystem is something like GPIO or video or serial. So you can have like a UART peripheral. It wants to go off, but the serial peripheral knows that in a second you're going to be sending some serial messages. And because the serial peripheral knows that you're going to be sending some serial messages, it wouldn't let your UART device go off. Although the way the device runtime power management is designed is so that devices themselves can say that, oh, I'm not being used right now, I'm not doing anything, I can just go into suspend. But it's the basic thing that they're explaining here is that the device itself is not the final say on whether it goes off or not. It might be, it might not be. There might be higher things in the software stack that no, but okay. So let's read here. Each layer, device drivers, subsystems, and applications can operate independently without needing to know about the specifics of the other layer, because the subsystem uses reference count to check when it needs to suspend or review or resume a device. Basically, it counts all the pointers that the application is using for a device, and if there is no pointer that the application is using for a device, it takes the device off. If there is a pointer, it keeps the device on, basically, is what we're saying here. And then there's below here, there's system managed device power management. I think this is the old school one. This is the old one. The system managed device power management PM framework is a method where devices are suspended along with the system entering a CPU or SoC power state. It can be enabled by setting config PM device system managed. When this method is used, device power management is mostly done inside PM system suspend. If a decision to enter CPU low power state is made, the power management subsystem will check if the selected low power state triggers device power management and then suspend devices before changing the state. The subsystem takes care of suspending devices following the initialization order, ensuring that possible dependencies between them are satisfied. So basically, this is the second one, is where the power management, like the going off and the going on, is tied to the SoC itself, the CPU itself. Like if you have a CPU and you have some way in your application, you tell your CPU go into low power mode right now, everything goes down with it. This is system managed device power management. And then whereas on the other one is like subsystems and applications and drivers can all decide by themselves, and they can all kind of agree to go off and on at the same time whenever they need. In fact, let's see if let's see if this can be, if we can make this actually work, the system level, system managed one. The first thing I want to do is actually make a gap enough here so that this sleep time is long enough. 1 second is still quite long. 1 second is still quite long, you know. 1 second is still quite long. But what if it's 10 seconds? Then we can notice it, I think. Because 1 second, I don't know how fast it takes to boot up the system, but let's try and see if we can make it do a power management with just let's actually bump this up. So let's go here and let's make this 10 seconds. 10, and I think I can do that in Zephyr. Can I? Bartlomiej, can I do that in Zephyr? Or do I have to do that? I don't know if I can do that in Zephyr. So 10,000. And then what I want to do is go back here, and then I want to enable this config PM device system manage. Config PM device system managed. Equal to yes. I don't know if this will work, but let's actually see. Let's build first of all, because that might not be possible with NRF, with the power domain thing, something. But let's see. Nathan is asking, why am I choosing system mode instead of the device mode? Because that's a simpler one to start with. We're going to do device mode just now. We're going to explore them. I want to do system one so that we can see how it works, and then we run it, and then we go back and we do our device one, and then when we know how to do the device one, we can enable power management in the MPU6050 drivers, and then when we enable power management on the MPU6050 drivers, we can now run it. Basically, I want I'm doing this like the way I do real apps, where you check that things are working as you're going, and you start with the simpler ones. So let's see if we can actually West flash that. Yeah. Sorry, that's flashed. Ooh. So config PM device. Let's see. Can we enable some logs? Config PM device. Let's also enable this so that we can see if like something is going to power savings mode and whatever. Actually perfect. So let's see here. And then let's actually West build. Turns out it works. I don't know what I tried last time. Maybe I tried too hard or something, but let's see. Okay. West flash. So I want to see here. Nothing. I don't see anything. Device list. Everything is ready. It never goes off. So actually, let's add a PM shell. Let's actually add a PM shell. Yeah, let's add a PM shell. Okay, so let's add the PM shell. Okay. Let's add the power management shell and see if we can do it from the shell, and we should be able to do devices, and we should be able to check. Okay. Let's see that. I want to do a clear. 1,000, 2, 2,000, 3, 3,000, 4, 1,000, 2, 2,000, 3, 3,000. It's gonna be on for 10 seconds, and then it's gonna go off. One 1,000, 2 2,000, 3 3,000, 4 4,000, 5 5,000, 6 6,000, 7 7,000, 8 8,000, 9 9,000, 10 10,000. Yeah. So the LED goes on for 10 seconds and goes off for 10 seconds. Okay, so what did I want to check? What I wanted to check now is whether, sorry, I just got distracted off screen. I wanted to check now is we should have device PM. I'm confused. Didn't we just enable power management? Okay, and PM device. So wait. Do I need to do more than that? I won't look at this yet. No, this is PM device. No, not that one. I want to see system managed. PM shell. I wanted to see shell commands here. device list PM. I don't see PM here. I don't see PM here. I don't see PM here. And device list. It's off now. So I don't see that. I don't see it going into, it's like this, it's like these things are disabled or something. Unless you're telling me I didn't save here. So let's cut here. Cut build Zephyr .config grep PM. So I see PM device is not set. Cool. Neither is. Do you see this? So it's not set as well. So PM power management is not set as well, because this is not set, but the one that we're trying to enable here. This is a driver. We'll get to that one just now. We'll get to the device one now. PM device system managed here. When this one is here, PM device system managed, it means it's being ignored during compile. So let's actually try and do that. It means there's a warning somewhere here that we're missing. Yeah. Warning. PM device shell defined in there, assigned yes, but got the value no. Check this unsatisfied dependencies. PM device. Okay. So PM device system managed defined at that was assigned yes, but got the value no. Check this dependencies that PM device is equals to no. So basically what they're saying here is we can't use PM device system manage. I think I'm now getting to where I was last time. PM device system manage is not usable. Okay. So this is being ignored. It's basically no. This is not usable. This one is fine. This one is okay. Yeah, so let's actually remove that one. So we know we can't use PM device. Basically, here it goes. PM device was assigned yes, but got the check this dependencies. The dependencies SOC series is that, SOC family is Renaissance, or PM device equals no. So that series or Renaissance, those are the ones that can do PM device system manage. Let's actually look at the config of it. PM device system managed. So selected by those dependencies on config PM device. Okay, cool. Let's SQ. So it looks like we have to do config PM device equals yes. Let's see if that actually built. So yeah, I see so PM device log is not labeled. It kind of worked now, but PM device log level. Why is that? Why is that a problem? Log. Why is this not working? Why is this not working? So, but no symbol ended up as the choice selection. Anyways, did we do our flash? So we need a PM device. Okay, cool. Then let's see. Okay, so there's that. 1,000, 2,000, 3,000, 4,000, 5,000. Okay, cool. Device tab. Yeah, so we have. So we have that. Device list. Device list again. Okay. PM. Suspend. So I don't even know which GPIO this is. Let's find out which GPIO we're using for LED. So we just need to go here. Yeah. LED 0, I think. Okay. LED 0, PMW add, LED 0. Okay, but which one is it? GPIO 2. It looks like LED 0 is GPIO 2 here. You see that? So let's try suspending GPIO 2. Okay. So let's go here. ls device list. Let's look at it. So device list, there's GPIO 2 here and it is active. Here it is. Suspend PM suspend GPIO at which one is it? 50. Device list. So you see it's suspended here. Amazing. Let's look at this. But this is funny because it's still working. It's still working. Unless I chose the wrong one. LED 0 is GPIO 2. This is green LED. Okay, cool. Green LED. Okay, cool. Yeah, green LED 0. That is GPIO 2. I'm pretty sure this is what we're using. Aliases. LED 0. Yeah, that's the one we're using for sure. This is funny because now device list. Cool. Device list. There's also the possibility that we can't actually suspend the GPIO peripheral itself, and then this is all happening through without so it's almost like a DMA thing. It's just like the GPIO peripheral itself is disabled, but how did it work? Why is it working? No. But Nathan. So PM. Suspend. Help. So you see, suspend the device. PM device. call the PM action suspend the device. I just suspend and then you choose the device. We chose this one, but it's not suspending. PM resume help. Okay, PM resume GPIO at 54504. So device list. Okay, so it's active. And obviously we're not getting the logs that we want because this is not config PM device log level debug. Okay, cool. So let's actually, can we just grab config PM device system manage, PM device yes, PM device so PM device log level, device log level, grab device log level. So this is not working. PM log level. Okay, so let's actually do that. PM log level. Let's PM log level. Okay, cool. So let's actually do that. Let's build it. I don't need another action, so I wanted it to I wonder if I can disable the GPIO but still have the GPIO pin turning on and off. What separation is there between the GPIO peripheral and the pin itself? And I thought if I disable the GPIO, I would cut the clock that is going to the GPIO, and if I cut the clock that is going to the GPIO, I wonder if that means I can still do things like write to a register and so on and so forth. Perfect. So let's do PM suspend GPIO at 555. We should see a log. We should see some sort of log, but we are not seeing a log at all. Debug is lowest, information 1, and then error. So this is actually in the where it's supposed to be. Config PM. Do you reckon? Nathan says I need to suspend the system itself as well because I'm using system power managed. Do I need to do that? Do I really need to do that? Okay, let's see. Device power management. Aha, you might be right. You might be right. So do you think we need to add power states? I wonder. Power. There's no power states defined, so perhaps I add this. So does this need to be in the, does this need to be, do I need to add CPUs and then add this? And I'm gonna be daring and do some stuff. I am gonna be daring and do some stuff. So what do I do with that? So I assume this is what is these two are the ones that are deciding whether we're going into power management or not and whatnot. Thank you, Nathan. Let's see if that actually works. Gonna say no. Can I go here? Actually, it's fine. Let's see, Nathan. Let's see. Bartlomiej, tell us what should we do, man? What should we do here, Bartlomiej? Since you're the one who brought this up now. Since we are the what how do you want us to experiment with this thing, Bartlomiej? Let us know. Anyone else with questions? Anyone with questions so far? I want to see cut CPUs, but I want to see B15. So I want to know where CPUs is in. What is CPUs in? Is it B50? I want to know what CPUs is in. Is it in like? Is it just in the root node? Anyways, from where? Can I go here and can I put that in? Can I do that? Can I do that? Bartlomiej never used Zephyr DTS. Okay. Okay, just fine. Bartlomiej has never used PM. Zephyr DTS vendor Nordic Doom. Okay, cool. So that's the one I want to find, and I want to know where CPUs is. It's in the chart. It's in the root. Okay, cool. So this is fine. I can modify it from here. Something like that. We'll find it. Don't worry, Bartlomiej. We're all learning right now. Nathan is teaching us. Okay, let's see. Does it go? Nathan was right. Nathan was right. Nathan was right. Nathan may have been the rightest person we ever knew. Device list. PM tab. PM suspend. We can only do those. So what's happening? I do not see myself going into PM mode. I don't see myself going into PM mode, even though we have some power stakes defined. Maybe we need to define some more callbacks. Let's go look again. Okay, so next thing that I've forgotten how to do. Zephyr idle thread. System thread. I want to use the idle thread. Okay, this is fine. I know what to do. I know what to do. I know what to do. I don't know what to do, obviously. I do not know what to do. I want to open this. PM system suspend. Why? Why are you lying to me? Why are you saying this exists? Do I need to build some sort of callback somewhere? Ooh, okay. Surprise. Days already a sample. Okay. Okay. There's nothing here. I don't see anything here. And that's just GPM. Okay, cool. Can we do that? Can we just run this? Samples boards ST. Oh no, this is ST. And no, this is device. I know this is device. This is fine. This is device. Device is easy because the driver itself implements these callbacks, which is easy. That's fine. Device is easy. What I'm trying to find out is system. So I want to see application. PM device policy. I need to define policies somehow. Can I see an example? Okay. Is this a full app? Both? Okay. You know, I'm a crazy person. So let's actually just test subsys power management. Test subsys power management. That. Can we copy that? Can we build that? So first, fucking hell. Okay, cool. So I knew that would happen. Let's look at this thing. Let's look at this. So basically, we have to read it and re-implement it ourselves. Okay, let's look at this thing. Is this okay? Cool. Is this a main? Okay, cool. I don't care about the device ones for now. PM state for state, and it's fine. It's fine. It's fine. Oh, I don't care about those ones. I don't care about those ones. No, PM device. This is device. I don't care about device. What I want to see is no, this is PM device. I would like to see a PM system managed. PM device, PM device. I want to see a PM system power managed, not PM device. Okay, cool. So that's not the one. That's not it. That is not the one. This is system power management. So you need config PM system suspend. Where do I need to implement PM system suspend? It's fine. I'm gonna find you. I am going to find you. I'm trying to find out how to get into using this system power manage thing. I don't want to use that one. I don't want to use the drivers. I want to just turn off the whole thing at once. Bartlomiej says we can we check the sample? Which sample do you think we can check? There's no power management. There's no system power management ones. I think this one is it. See, here's the examples. There's no. We can look at samples. We can look at samples. Which one is this power switch? This is the one I just opened. I would like to keep that one. Okay, cool. So let's go here, Zephyr, Bartlomiej. Let's look at it. Samples. The thing about power management is it's quite different. It's quite different between many vendors. So you might not even find a sample that works with the NRF power management. There's device PM. Okay, so this is device PM. I don't know about that. Source. Let's look at it. Main. This is device power management. This is fine. We'll look at this just now. Let's look at latency one. The latency one might be the one that we want. So basically, what happened here? Config PM, config log, yeah. Source PM. Sweet. Thank you, Bartlomiej. Okay, so let's run this one. Samples, sample subsys PM latency. So let's look at that one. Okay, so that one works. Let's actually explore that one then. Well, I think it works. Okay, so let's actually go into that one and try and modify it. Okay, so subsys PM latency. So this one, I guess this is called latency because it checks how long it is before an action needs to happen, and then it suspends based on that. So the first thing I want to look at is the project conf. It's just config PM. Config PM is what? Config PM does what? Config PM. Such kconfig. System power management. This option enables the board to implement extra power management policies whenever the kernel becomes idle. The kernel informs the power managed subsystem of the number of ticks until the next kernel timer is due to expire. Okay, cool. So the thing that happens here is the kernel tells the Zephyr kernel tells the power management subsystem the next deadline. Zephyr API, kernel APIs. If I remember correctly, there's a deadline one. There's a deadline one. Let me see. K time I need, K time expire. Yeah, so there's this K time expires, or rather, you can actually look at K timer remaining ticks. So get time remaining before timer next expires. So the kernel is going to go through everything it has waiting. The kernel is going to go through everything it has waiting. And let's look here. So the kernel is going through everything it has waiting. So let's look at main. Probably should be short. Oh yeah. So there should be like a sleep cycle somewhere, or a wait cycle somewhere. So if latency cease equals forever, this is microseconds or US, latency constraint change, none. Log info latency constraint, however many microseconds. Okay, cool. So in main we have first of all we have PM policy and we have sysclock, but PM policy looks like the thing that we need. PM policy.h. PM policy, we can actually look for it. Let's actually look at what that does. Is this API? PM policy. Policy.h. Yeah, cool. Should be in PM. So no. Policy.h. So this should be in Zephyr PM state. PM. This is P state. Okay, we'll find this. We can go find it in the code itself, but it's fine. So right now, let's look at this. So we include Zephyr PM policy .h, and then that provides us this PM policy latency subscription and a PM policy latency request. No. So start PM policy latency subscription latency request. Would this be what I'm? No, this is the name of the thing I'm calling it. This is the name of the thing as it's called. Let's go find out PM policy. It's actually fine. Let's actually use this. I want to take that, copy, and then I want to go in here and I want to go like, give this to me. Where is this? Zephyr PM policy.h. I knew it would be there. So this, okay, cool. Brief latency subscription, change subscription. Latency change subscription. Latency, delay. A latency is a delay. All fields in this structure are meant for private use. Okay, so latency is a delay. Latency is a time delay between the cause and the effect of some physical something. Okay, cool. So far, that's fine. So we subscribe. This is a subscription to a latency delay, and this is a request to a what? This is a request to a what? Where is that? So latency request. So I'm asking. I want you to wait 1.1 seconds, and I'm subscribing to you to tell me when that wait is done. That's the two of those. That is both what both those two things do. Okay, so let's look at it. Device get binding dev test. If device is ready, log error. Device is not ready. Cool. So this could be our GPIO device. Okay, whatever. PM policy latency change, subscribe on subs on latency changed. On latency change. On latency change. So on latency change, this takes an in32 latency. If latency equals to sys forever US, this is a macro. This is just K forever, I think. That is just K forever, I think. That system-wide micro to denote forever in microseconds. So this is something that says k wait forever. So if like if you have like a thread that waits forever for something, you know, it doesn't start. When you say wait forever, it means don't start until some condition is met. Okay, cool. So if the latency is forever, log in for latency constraint charge none. Okay. Else if it's anything else, latency constraint change, it's that that is 32 bits microseconds, latency of USEC per MSEC, nanoseconds per millisecond or something like that. Okay, cool. So 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 you make a subscription, you subscribe to whatever. Can I make this in Blinky? Can I move this to Blinky? Can I move this to Blinky somehow? And we get it working with Blinky. Yeah, let's put this in Blinky. I'm gonna open this. Which one is this one? Which sample is this? Latency. Cool. Let's put that. No. What? Ooh, I see. See make list? Does that use source all.c's? What does test.h? Just a moment. I'm trying to understand how this works. So we should enter, we should enter, we should enter. That's fine. Nothing happens there. Okay. Setting that, we get that, that's fine. Sleeping phone. Yeah, but I'm not seeing. I'm not seeing these devices. This is just the logs from the thing itself. It's just the logs. That log just comes from here. It doesn't. I don't see something. I think so. I think I understand. I think I understand. So, okay. I think I understand. So, this if this is less than this, does that mean what happens if this is 5,000? Does that mean okay? What is runtime idle? What is suspend to idle? What are those? What are those? What are these? Are these PM states? Are these PM states something that just Zephyr knows? Okay, cool. So PM, I don't see entering anywhere. You see that? I don't see entering anywhere. I see app, I see dev test. I don't see entering anywhere. Entering. So this is fine. So for some reason we're not going into PM state. Let's look at boards. There you go. These are the things we need. let's actually do app.overlay. Okay. It's gonna explode a little. I understand now. I understand now. Yeah, I understand now. Nathan, how did we add the other power states in the beginning? Here, CPUs. Okay. I'm just gonna remove this. I understand now. I don't even know what power management right now I'm using, but CPUs. I don't even know if this is and it oh, this is amazing. This is amazing. Look who wrote it. So this should work. Let's see. Seven. Okay, cool. So let's actually try that again. I still don't see the entering part. Do you see that? Next thing we're gonna do is actually cut this thing for power states. Okay, let's do CPUs. What if I go like it's still not finding the power states at the moment. Okay. Okay. what if I go then, this is what does it say if I have that? Okay. 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 So let's actually be clever a bit again. Let's actually be a little bit clever and run this for excuse me. Native C. Yeah, you see it's doing it now. It's doing it now. See, it's doing it now. It's doing it now. Okay, cool. So the first thing we need to find out is how to make this work for the board. Power state. Okay. Aha. Can we do this? So this is gonna fail at building. That's fine. We want it to. This is okay. I want it to fail at building. No. I want it to fail at building now. This is good because the node CPUs was not found. CPU at so okay, cool. So now remember we have a CPU at 0. I think so. I think if we build that, this might now actually work. Let's try that. It's okay. We'll find it. Oh, actually no. We don't even have to look here. We don't even actually have to suffer that much. There's a place that we had opened this. Yeah, CPUs. CPU up. Okay. I think this is also the one we're building to. I think so. This is what we're building to. CPU up. We are building to CPU up. I'll just clear it. See, we are building to CPU up, so we did add those power states to CPU up now. Fingers crossed this one works. Perfect. West flash. Perfect. So this now should give us just a moment, let me find it. Doesn't matter really. I should know how to use this by now, but I keep forgetting because I use it so rarely. Okay, so here, just wanted to do this is other to line dash e build Zephyr Elf, and then I need to use this to know what crashed. Pretty tough, but crashed. But it worked, yeah. Okay, so let's just do all of them. Okay, and then I want to do that, and I want to just paste all of the ones in, all of these other ones in. So that one, no, this is bad. Copy. Okay, that one's bad. This one might be a valid one. Okay, just one moment, copy, yeah. Okay, so let's see. CF register log, init C, free remove, free remove, free remove. CD heap. So this is probably because either because it's NRF power, I'm a little confused now. This is either because NRF power is failing, because this is hip stuff. So this is basically a memory thing somehow. Was it too big? Was it big? This also can tell us what the issue is. We could have been calling like either an illegal address. Well, something is too big for this. Stack overflow on. We have a stack overflow on CPU 0. But nothing's changed. Nothing's changed from here. Okay, so let's actually just try and reduce these latencies by 10 all by 100. But these are USs. These are USs. That I don't see how that's a problem. Yeah, this is I don't see how that's a problem. Okay, so first of all, we understand what we need. We need to implement power states, and these power states need to belong to a CPU. And once we can give these power states to a CPU, we can invoke them. We can invoke them as here. So basically by when we set this sleep here, this is why it works for native, by the way. This is why it works for native. I want to rename this. Okay. I want to rename this to sun. Because this is why it works on if we build it for native sim, you can see it works here. So the problem is, how do we make power management work with the NRF? And where is the issue? So if I go here and I just run this, you can actually see it does the thing it's supposed to do. Sleeping for 1.1, we should enter runtime idle. So there you go, entering runtime idle 0 from SOCPN. Sleeping for 1.2 seconds, we should enter suspend to idle. Perfect. Sleeping for 1.3 seconds, we should enter standby, entering standby. Setting latency constraint 30 ms, latency constraint change 5 ms. Sleeping for a while, we should enter runtime idle, we don't. We should enter suspend to idle, we don't. We should enter suspend to idle, we don't. So basically, because we're setting the latency to 30 ms, and this is too small this is too small to affect that. Okay, adding latency constraint 20 ms, we should enter runtime idle, we don't. We should enter runtime idle, we don't. We should enter runtime idle, we don't. Okay, cool. 10 ms, we should stay active. We should stay active, nothing happens, cool. And then we go into the app, updating latency constraint 30 ms, latency constraint change 20 ms, 20 ms, cool. So we're using the test device. Okay. Closing test device, removing latency constraint. Sleeping for 1.1, we should enter runtime idle. Sleeping 1.2, we should enter suspend to idle, and we do enter those, removing latency constraint. So let's actually look at this second set. Why aren't we getting into here? Why aren't we getting into that? So basically, Bartlomiej, this is what we will need to do in our device. We will need to build these policies. We would need to build these policies, and where is the dev test? You need dev test. This is the device itself, dev test. This is the thing. This is a init. This is a null and data. Where is power management? Okay. This is what we would need to do for our device, but we will get there. And main first of all. This one, testing without any latency constraint. Okay, So these ones actually trigger runtime idle, suspend to idle, standby, and those are because those ones are here. The first ones, runtime idle, suspend to idles, entering standby. And why are those ones working? Because if I go into boards and I go into the overlays, exit latency is in US to so I could jump between both of them like that, yeah. So if I go here, okay, and if I go here, KM sleep is microseconds, 11. US to MS. So 1 millisecond equals to 0. On the outside US. Okay, it's a U controller, so it's a microcontroller. 1 millisecond, or rather, let's go this way. No, let's actually do this way. 1 millisecond to microsecond. It's 1,000. So KM sleep of 1,000 is 1 million microseconds. Okay, cool. Release, so let's go back here, and this is 1 million mean residency US. So my minimum residency US, we were here. Residency managed. Just one moment. Is this starting to make any sense? Does this make any sense? I'm starting to see the sense here. So I think this is a residency system where we have residency. Under the residency policy, the system will enter the power state which offers the highest power savings, with the constraint that the sum of the minimum residency value, this is Zephyr power state, and the latency to exit the mode must be less than or equal to the system idle time during duration scheduled by the kernel. Okay, cool. So look at it this way. So minimum residency duration in microseconds. How much time the residency in a given idle state must last for the state entry to be worthwhile energy-wise. It includes the time to enter into this state and represents the break-even time to justify the state, the power spent on the work needed for entering and exiting the state based on how much actual energy is saved once in the state comparing to choosing the next shallowest step. So I see how it's working here. I see how it's working here. Look at it this way. I see how it is working here. So this is 1 million. This is basically 1 microsecond. And then the exit latency is 10,000. Exit latency. What is exit latency? Worst case latency in microseconds required to exit the state. Okay, cool. So that doesn't matter. It goes like time to next scheduled event is greater than or equal to state minimum residency present exit latency. Okay, cool. So this is in US as well. Okay, so to get in here, 1 million. So minimum residency, this is runtime idle. Runtime idle. Why would we? So this is 100. Basically, this is greater than. So this to microseconds. This to microseconds. It's 100 is that. So this is bigger than. That is bigger than. That is bigger than 1 million plus 10,000, because 1 million plus 10,000 is 1, 2, 3, 4, 1. So it would be here. So 1.1 million is greater than 1 million and 10,000, and that is why it gets into here. Okay, so here minimum residency is 1.1 million, which is the total time that's set in the other one, and then the exit latency is here, so 1.12. So, and the other one, the next delay is 1.2. 1.2 million is more than 1.12. Yes. So we should enter that. Okay. Adding an application level latency constraint. PM policy latency request add. Cool. PM policy latency request add. Okay. Somewhere in here we should find that. PM policy request add. This looks like a device one. This looks like a device. Yeah. Okay. The system will not enter any power state that would make the system to exceed the given latency value. Add a new latency requirement. The system will not enter any power state that will make the system to exceed the given latency value. I'm trying to think about it, because okay, I'm trying to think about it. How does that one work? So this is the first one. This is okay. This one we understand that one. And then the application level constraint is setting the constraint to 30 ms. The system will not enter any power state that would make the system to exceed the given latency value. That is 5,000 microseconds, which is nothing because the other ones are in millions. If we do 5 million, okay, cool. So I have an idea here. If this was actually pushed up to 5 million, then this one should work. It works. It works. Look here. So it works. So, oh shame. I understood that, and then I don't know why I understood it. Now I don't know how I understood it. Now I need to go and understand it again. Okay. So I kind of understand it now. Basically, when it is this, when it is 5,000, we don't actually, the application, this means the application now is saying don't enter a power state unless it is cheaper to enter and leave for 5,000 microseconds, basically. And all the power states define that you need something like 1 million microseconds to get into them. That's the least one. That's the one that is the least. And basically what is happening here is that because it says it needs 1 million and the application says no, do not change power state. So this is kind of like what happens if you have like you have something that you're expecting in the next 5 microseconds and you don't want the system to change power state because you don't want it to go to idle in case this signal came in. In case this signal came in, you don't want the system to go to idle or to go to another power state because it's expensive. If the signal comes in and you're in another power state and you have to come up from the other power state, it's going to be quite painful, quite expensive. You don't want that to happen. Cool. So you set an application level constraint. Okay. Now I understand. Now I really understand what's happening here. So here you set an application level constraint, and that prevents the application prevents it from going. Okay, and then open when you set the device as well. The device as well. It sets a 2001. So they're doing MS here, but it's wrong. It's at a 2001, and the 2000 MS is too. Also, so what they're showing us here is that the device, a device driver can go like, hey, please don't go off for this amount of time. Please don't go off for this amount of time. And they've also shown us that an application as well can go like, please don't go off for this amount of time. So basically there's those two. Okay, there's those two. Both an application and a device can go like, no, don't go off. And the system will respect that depending on the policies. Okay, cool. So then we go here, we want to return it back to the 30 ms. So this is actually 30,000. This is actually the 30,000 that it was before. Okay, so this is something. This goes back to what it used to be before. Okay, so it looks like this requests, the request add uses a different unit than a request update, actually, because request update actually fixes it, because we go back to actually going to them, like as you see here in the bottom, we actually do end up switching SOC entering that, SOC entering that, SOC entering that. Okay, so it looks like update, policy request update, and add use different units. Let's actually look. We may have discovered a bug in Zephyr. So this is UIN32 value US and UIN32 value US. We're supposed to pmpolicy.c. We're supposed to implement this. Let's see. Okay. We're supposed to implement that because I don't know where it is. I don't know where that implementation is, and this is not an inlined one. So someone is implementing policy.h. Oh yeah, some of them are here. So somewhere else these are being implemented, and that ends up being how request does the wrong amount and update does the correct amount, basically. Because when we call update here, it goes back to enabling them in here. So this is basically how you do it with system, what is it called? Where's that one? Where's the big flowchart? This is how you do it with system power management. This is actually now system power management by itself. And this basically allows you to suspend the system or wake the system when you want. This is SOC level. So this is actually discouraged, to be honest. This is discouraged. I'll show you someone. We are discouraged from using this basically. Let me show. Where does it say that? Where does it say that? Let's go back. Note, when using this method of device power management, the CPU will not enter a low power state if a device cannot be suspended. For example, if a device returns such an error as EBZ in response to the PM device action suspend action, indicating it is in the middle of a transaction that cannot be interrupted. Another condition that prevents the CPU from entering low power state is if the option config PM need all devices idle is set. It is important to emphasize that this method has drawbacks. Device runtime power management is a preferred method for implementing power management. Does anyone have any questions right now? It's been 2 hours. We found out about system power management. I'm wondering if I should go on or we can go on with this one another day. Because we can also look at device power management, I think. And I think that's gonna be quite easy and quite better because this has revealed quite a lot to us. Okay. Does anyone have any questions at the moment? Anyone, any questions at the moment? No questions. No questions at the moment. So okay, let's look at the samples. Wow, wait. Wait. Nathan, when did you say I should implement the temperature sensor? Just now or 5 hours ago? Nathan's gone. Bartlomiej, are you still here? Yes, let me see. I wasn't looking at the chart and then I kind of disappointed you guys. Now I'm feeling bad for it now. I dropped down a bit too far. Okay, cool. Sorry. So Nathan says there's a delay. Sorry about this. Let's look at the chart. Okay, so let's actually just go to. Sorry about that. I don't know how I fell out of sync or something, and I kind of got carried away with exploring something. Okay, so device power management. Let's look at device power management and look at source, dummy driver, dummy this. Okay, cool. So let's actually run device power management for the thing. Let's see if it runs, and if it runs, let's actually implement it. So this is latency. We've looked at latency. PM. Okay. PM latency. Okay, it's fine. PM device power management. Yes, I'm going to share the code, but there's not really any code that I've done right now. Maybe now it's when I'm going to start the code 2 hours in. But let's see. Okay, cool. So it runs on this. Let's actually do a west flash. I want to know if it runs, and if it runs, we can actually cool, perfect. Here we go. Device power management sample app start, parent resuming, child resuming, device dummy device resumed, child suspending, parent suspending. Cool. So this is now the new. This is the recommended way. Okay, sorry about that. I'm frustrated with myself. Like we read here, this is the preferred way. Device runtime power management is the preferred way for implementing power management. So let's look at it quickly, and then we start implementing it for our temperature sensor. So let's look at it. So main is fine. Main doesn't need much to be done. This is okay. Main doesn't need much to be done. With device power management, you don't need that much to be done. What you actually need to do is dummy driver.c, something like that. What we need to do is implement this power management actions. This one's over here. This one's over here. And the way device power management works is that whenever the system senses that there shouldn't be any, there's not going to be any device tree, anything here or whatever, if I recall correctly. It's basically you're letting the system decide that the device is not in use, and once the device is not in use, it can basically suspend the device. And if it can suspend the device, then you basically are doing something else. And the way we achieve this, the way we achieve Zephyr device power management, is just adding like a callback. We need to add. This is a dummy driver, but what the thing that you need to observe here is the PM suspend, PM resume, PM turn off. All of these are the sort of like the things that we need to do in order to basically make this work. So the first thing we can do is add these callbacks to the device driver that we need to use. The device driver that we need to use is the MPU6050. This guy. Let's actually hook that up. So actually we need VCC, we need ground, we need SEL, SDC, SDL, SEA. I don't know if we need the interrupt pin. So let's actually look at it. Do we need the interrupt pin? I don't know if we need the interrupt pin. I just want to check that if we need the interrupt pin. I2C, Axel, MPU, if enable config MPU trigger. We can go without that for now. I think we can survive without that. So let's ignore that. So let me hook this up. I just need I need four wires, 4 female to females. Female to female. No. 1. No. I need for female to female, female to female, female to female, 2 3, female to female, 4. Okay, so the next thing we need to do is we need to discover which pins we want to use. So I squared C, what I want to know is which I squared C pins are being used actually. Which pins are I squared C? So is it this one? Can I go here? Zephyr boards. NRF54L15. It's gonna. Here's the thing. Doing the sample is going to be like 15 minutes. The issues where if you don't understand, but you guys know this already. You guys know this already. CPU up DTS. L15 CPU up DTS. Okay, cool. I want to know I squared that's the common. CPU up DTSI. L15 CPU up DTSI. L15 CPU up DTSI. There's no DTSs here. Okay, so where's the common one? Common DTS. I would like to find I squared C. No, there's none here. So I want to find this one. No. Just give me a moment. I need to find this file. I need to find this file. I don't know if it's gonna be from Nordic or from Zephyr. So let's actually just find it. I'm trying to find out which pins map to which one. Which pins map to I squared C, so that I can just use that immediately. Okay, cool. There you go. Okay, L15, Nordic L15. So let's go back. Sorry. So this is include 05, 10, 10, 15. This one, CPU up DTSI. Cool. Okay, cool. So now CPU. Okay, cool. I like the flipper CPU, but we'll get to that another day. I would like to find I squared C. Can I find I squared C? No. What can I find any includes? There's no includes here. So cool. So let's look at the other one. Nordic L15, L54. Yeah. Okay. L54. Bartlomiej, do you know the pins? Bartlomiej, do you know the pins for I squared C on this board? No, man. Seriously? But I already looked at that. 05 or 10. ISO1. CPU flippers off, SoC is on. I2C, yeah, it's gonna be here. I2C, oh, fine. This is here. Okay, I2C 20. Okay, cool. So cool. I2C S2C. So which pins? Which pins? I would like to know which pins are being used here. So okay. I need the pin control that is going for here. Man, this is why I don't. Okay, don't get frustrated right now. Do not get frustrated. Find this file. Find this file. Okay, sure thing. I need to know which pins are on I2C. I remember this being very difficult. I really do remember this being very difficult. Okay, cool. So this is the DTSI, and there's no pin control in here. Let's see pin control. There's no pin control in here. Yeah, sure. I2C is that one. There's that one. That one. Okay, cool. C700. Yeah. Let's just copy that. No. Copy that. I know what I'm gonna do now. I remember this being insanely difficult. Okay. I see 20. Okay. No. I need to find. Okay. I don't care. I just need to find this. Oh, perfect. Thank you. Bartlomiej shared the pins. So, okay, let's hook it up. What's that? Which I2C is this one? Do you know? Bartlomiej. Which I2C is this one? Okay, we can just scan both of them and it's fine. We'll find it. Okay. It's okay. It is okay. P112. Okay. Okay, so first of all, let's actually get all of this. VCC goes to VCC goes to somewhere, VDDIO, okay, VDDIO is fine. Okay, and then the next one is what? Ground? Yeah, that's fine. Ground. Okay, the next one is what? The next one is what? What is the next one? Yellow is SCL. Yellow is SCL. SCL is P111. Okay, and then I see SDA is P112. Okay, so which port is this one? We just need to scan both of them. Okay, it's fine. $22. Okay, cool. That's the overlay file. Thanks for giving it to me. I'll use a Hello World one. I'll use Hello World. Okay. I'll use the Hello World app and then I will share it. Samples. Okay. Basic. No, samples Hello World. There should be a Hello World one. Just one moment, guys. There should be a sample that is Hello World somewhere. Yeah, Hello World. Here it is. And I'm gonna make a app.overlay. Okay, and then I'm gonna copy the overlay that Bartlomiej has provided, and then here I'm going to enable config I2C, and then I'm going to go config I2C shell. Okay, this should be okay. So let's actually build this. Where did you find those pin definitions? Did you use the something in the Zephyr connector SDK or whatever? Zephyr samples world -p. Let's see. Okay, cool, perfect. So where's the flash? Oh, actually, it should give us. It should give us. I'm sorry. So config shell. Yeah. I think first flash. It's gonna rebuild. Let's see if we can get something. Okay. Okay, cool. So I wanted the I2C I2C thing, I2C scan, no devices. What is I2C22? I2C. I2C. C800. So it should actually be there. I do have an LED on the. I do have a power LED that's it. Okay, cool. I found the issue. One pin was disconnected. Okay, cool, perfect. I think we can hot plug like that, and it should have something. Where's the reset button? I2C scan. No devices found. No devices found. So we say SCL is 11. Yellow is 11. Port 1, yes, port 1 is 11. 10, 11, cool, yeah. And then SDA so we should see a device there, that's the problem. We should see a device there. Yep. Bartlomiej. Yep, I'm doing the same thing. And there's a power LED on this thing that says yes, it's powered up. Are there any other jumpers that I need to select? I shouldn't need to select any other jumper. Man, why can I never get a simple life, man? Where stuff just works. I'm pretty sure I'm doing some silly mistake. Build log? Yeah, sure. Build logs are going okay, Bartlomiej. No issues. I'm talking to Bartlomiej, who's on Discord, by the way, if anyone is wondering. Build logs, there's no issue in the build logs completely. Everything's going okay. Yeah, I built it. I can clear again. I can rm-rf build, and I can actually build now. There you go. Nothing. Everything clean. It uses the app overlay. It finds the app overlay and it uses it. Cool, and it's there. If I do a West Flash, it's actually good because here you can see it goes hello world, which is the hello world app, and then I can do ITC scan that one. There should be a device there. Do I have a quick accelerometer? Just hold on. I should have. Okay, I'm just gonna check or something. Okay, I think this is I2C. Yeah. Oh, yeah. So I have another device. I'm gonna check with the other device. Disconnect maybe. Sure. I remember that. I remember that interview. Oh my god, I'm dying. Yeah, that dude killed someone, and then I was like, oh no, someone told me to kill him. Oh my god. Screw you, Bartlomiej, man. Oh. Wait. Wait. Bartlomiej, does it say P1 VDD IO there is 1.8? That could be the reason. I think I need 3.3. I think I need 3.3. So let me see. Where do I get 3.3 on the board? Man, don't tell me I need to go and get oh, come on. Do I need to get a multimeter to check? Pull-ups? No, I don't have pull-ups. They're on the thing, they're on the device itself. Do I need pull-ups on a dev board? I shouldn't need pull-ups. Man, fuck this. Okay, cool. Let's just check. I'm pretty sure I need 3.3. Bartlomiej is basically saying I'm the reason it's not working. I'm okay with being the reason it's not working. Yeah, that's 1.8. Yeah, that's 1.8. That's too high. That's too high. That's too high. Okay, cool. Yeah, temperature sensor. Yeah, it should have, yeah, because it's a dev board. It's a dev board. The temperature, yeah, it should have. It should have. How do I get 3.3 power on this thing? It's like an FPGA. I can only get I have a level converter, but I don't want to use a level converter right now. This is crazy, man. How do I get 3.3? No way they did that. No way they made it impossible to get 3.3 without a level converter. Okay, so MPU6050, that is what does it need? Why can't life just be like straightforward? Just be like, oh, man. What power does you need? What power do you need? Yeah, you need 3.3, and that's why this thing is not working. That's why it's not finding the device. And I don't know where to find 3.3 on this board. Oh my word. I need to switch something. 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 There's something I need. No, I do not have that tool. I do not have the. Fuck. Is that the board config? I hate this people. I hate this people. So I hate these people. It's basically I need the NCS tool. I hate these people. Why? Why would you make a 3.3 board that I need your software to change? Why would you do that? Why would you do that? Why would you do this? Why would you make it that I have to install software to use? Man. It's fine. Nah, it's fine. It's fucking fine. All that. I'll get the app. Now I have to download software to use a board that I have. Man. How much? 100, 200 MB. I don't care. It's not even that much. I don't care about that. It's just like, that pisses me off, man. I should be able to use 3.3, man. I should be able to just use 3.3. What? Can I use this thing on their website? Sure. Nah. I'm just gonna start swapping while that thing downloads. I hate it. What? I mean, they should make it. I should be able to use a jumper, man. I should be able to use a jumper. This is so unfair. This is so. This is such. Yeah, man. Yeah, man. Not even. Not even. I have a. Can we an XP? While we wait for that thing. Can we do an XP? While we wait for that thing. I'm just, this is unreal. Why? What? Why? And they knew exactly what they were doing because they gave you 5V and they gave you 1.8V. It's like either you're doing FPGA stuff or you're doing Arduino stuff. But if you're doing anything 3.3V, which is what everyone uses, you have to get our software. What the heck? That is just madness, man. Madness. I'm telling you. Utter madness. In the meanwhile, let's see how long. Let me show you. Let's see how long it will take me to swap CPU. Yeah, let's see how long it will take to swap CPUs. I'm gonna jump on I need a female to male, 4 female to males. Okay, and what I'm gonna do now is I'm gonna get the thing going. Yeah, bullshit. Yeah, bullshit. I see that, Bartlomiej. Not your fault, but their fault. Bullshit, though. Bullshit. Check how easy they lose people. Yeah, I get a different board that has 3.3. Why do I need 1.2? Why am I gonna use 1.2? Why would you ever do that? I get a different board that has 3.3. Plug in my sensor. Where's my sensor? I lost my sensor. What the heck? I lost my sensor now. Plug in my sensor and I'm off to the races before I finish downloading that thing, and I convince my client to get. It's fine, man. It's fine. SD has Bluetooth. SD has Bluetooth. It's fine, man. It's actual bullshit. Actual bullshit. Let's actually do this. We're gonna get power management before that thing finishes downloading. Yeah, maybe it's my fault. I have slow internet or whatever, but I have fast enough internet to stream. If I do this while setting up a proof of concept, then I'm out, man. First thing that works. What the heck? What in the world? I am mighty pissed off. I mean, I'm not gonna shout at them. Their samples don't work either. There you go. Hooking this up to FRDM, MCNX, MCX, MCNX, What the heck is this thing? FRDM, MCX, enter M236. This is gonna run 5 minutes. I'm gonna be doing power management just right now. Just check. Okay, cool. Okay, cool. Board configurator up. What the heck? What is this? Red. This is SCL. Okay, cool. What in the world? No, this doesn't work. Okay, so that's in. And then the next one is what? SCL. No, this was wrong. Red is SCL. Actually just use this as well. I can use this one too. P40, P41. There you go. And then that's the P40 is what? P40 is SDA. P41 is SCL. Okay, cool. So P40 is SDA. Still downloading. P40 is SDA. Before one is a CL. Okay, and then what else? And then ground. This is ground. This is power. So purple is ground. Blue is power. This is ground. This is power. Yeah, man. I don't think radio is that like amazing that you have to make it hard for people to use your devices. Check. I'm already connected. Disconnect that one. Even uses the same cable. And then I'm gonna go into my code here. I'm gonna go into my code here and up overlay that, and I'm gonna remove this. That's even worse, because check. Let's go see. Okay. Let's see. It's going to be FRDM MCX and 236, yeah. While that builds, here's MCU link. Cool. Yeah. I have link here on it. So there you go. West flush. Are you gonna find it? Yeah, okay, so that's flashed. Okay, fine. CM1? No. CM0? I2C? I2C scan? LPC, I2C, LP. Okay, 5800. B5800, B5800. Nothing. 9. 6818. So let's see what is the MPU6050. What device is it? What is the MPU6050? MPU6050. 6050. But what address is it? What address is it? Oh, you can actually power it with a 5 volt, but I don't know what that would do to the thing. What address is it? What is the I2C address of this thing? ITG datasheet. Yeah, so that's how it goes. So that's really, I'm really bummed. I'm still waiting for this thing. Address. Depends. Okay. Oh wait, I can read those now. This is like, this looks like 18 to me, but that's 1-1. Okay. Well, it's definitely not this one. It's not 68. This is yeah, cool. So let's actually see. Yeah, whatever. Ah, fuck. 68. How is that 68? Oh, okay, that is 6. Idiot FPGA developer that cannot read binary. Cool. So we found the device, and it's on LPC. What is it? Where is it on? There it is. So first of all, let's actually get in here. While this is still downloading, whatever, 500 MB for or 100 MB for whatever. Oh, okay, cool. So now let's actually just do let's actually set this device up and we can get to reading it. FRDM MCX and 236. So that's, I just need to find out which I squared MCX. Just give me that. Yeah. Huh? No, this. Come on, just remove all of this. Is this Bartlomiej in the room with us? The problem is me, guys. The problem is me. The problem is always me. That's it. Okay, cool. So let's see. I wanna get here. I wanna see the board sources. I wanna know DTC. DS. I would like to know I2C. Which one are you? Huh. Bruh. I know how to do this. I can find you. Don't worry. Device list. Which one is it? This one. Okay, cool. So that's fine. Okay, no, I don't care about you. Okay, status. This is already fine. It's just, I just like doing it. And then I want to go back here and I want to do MPU6050. Please just give me the that's fine. Please just give me that. I would like to find the YAML. Give me the YAML. The YAML or an example. That's fine. This is okay. I want this. I can task. I don't know what that means, but I'm not gonna mess with it right now. Okay. We can almost start doing low power. It's been 3 hours. Okay, fine. Now I get why people do this all the time. Okay, cool. That's fine. What do you expect? Still, download going. Okay, let's see. This better become Zephyr pull request. Yeah, cool. Let's see if everything goes okay. If everything everything goes okay. Device list. There should be an MPU6050 somewhere there. Nah? Nah? For reals? Syscon, FlexCon, FlexCon, FlexCon. Ah, I see. I know what. I know why. I know why. I know why. Config sensor. Config sensor. Yeah. And then what config MPU6050. Yeah. Config. I was reading a thing yesterday by Sean Hymo about like the hidden dangers of so that's fine. Let's I was reading this thing yesterday by Sean Hymo about how Zephyr can sometimes be, you know, let me open. There's this document by Sean Hymo. It's about like Zephyr can be tricky. Zephyr can be tricky because if you don't know all this, so you can get this link somewhere. Hidden cost of using Zephyr, the complexity of the build system, and these are things you just get used to as you go along. And I can see the like the advantages for me right now because I know where to check for things that are not working, and you know, it's easy to find them. Not that it's working now. Where is this sensor? Why is that sensor not here? Do I need to do like a complete off and on? I don't think so. Device list. I2C scan 9. 68 is there. 68 is there, and this one is flexcom I2C2. Okay, so that is there, and this is here. I'm kind of confused now. Ah, there you go. It's here. Why did I not see it? Why did I not see this thing before? Okay, cool. So now this is initializing and it's there. So the next thing we need to do now. Is basically I think there should be like a sample somewhere for sure. There's a sample somewhere. There should be a sample that shows us to use this. I don't really care about it. Still downloading. I've already done the proof of concept with a different device. Okay, so there should be a sample somewhere here. There should be a sample somewhere. Sensor sample somewhere. that shows like reading something. Isn't there? Yeah, convert temp. This is what I actually want to do. So sample sensor. I'll just go to main. Why am I here? Well, I'm just confirming that it works, and then we can move on to actually doing the power management. You never want to like just plug on with the code and you don't know. Samples. Yeah. Do they make an MPU6050 here? Be nice. Okay, cool. So there is a MPU6050 sample. Why? So let's go back. Okay. Okay. Let's conf. Config I2C shell go to Y config shell so here let's build samples sensor MPU6050 should go. Okay, now let's flash. Okay, let's see. Device list. Why? Why is it disabled? I think I'm going to remove that. I don't get why it's disabled. I think it was because of the GPIOs. Why is it disabled? Config MPU config 60 MPU 6050. Yeah, this is why you have to kind of like make sure everything is working fast before you start modifying code, because you start modifying code and then you get so fine and you don't know if it was working before you started, and then basically you end up at a place where it looks like it feels like you don't even know if it's changes you've introduced or device list. What? I think today's. I think I shouldn't try code today. Okay. Okay. I2C scan 9. Nothing's disconnected. It's all here. All here. It really is all here. I'm gonna stop soon. I'm gonna give up. Okay, wait. Is this thing finished? What is happening today? What is this? Guys, I have to stop. I have to stop. Okay, there's one more option. Okay. I can just go in here and I can take this. No, this is I don't care about this. Yeah. Let's look at this. Yeah, remove this. Made by Nordic. Okay, so let's try some bullshit again. Okay. Let's think you're doing some silly thing where you're using you're trying to use something like yeah, that is the one I'm using. But this was working just now. Was that written? Okay. Yeah, sure. I'm not gonna go fix Zephyr right now. Okay. Device. Okay, so I burnt out the device or something like that. I basically exploded the device or something like that. That's what I've done. Somehow I've destroyed the device or the board. I'm gonna have to stop sometime today. I don't want to stop though. I do not want to stop because this is it's been a 5-hour stream now. It's doing the thing it's supposed to do. Okay? It is doing the thing it's supposed to do. It's doing the thing it's supposed to do. And okay, cool. So that's fine. So that's fine. Okay, fine. So it works. It works now. It works now. It works now. It works now. Let's not get too angry about it. Let's not get too angry about it. Okay, let's not get too angry about it. We might even go just implement the things right now. Okay, cool. got the software for that thing, and it's still I still have to get more software. That's kind of like nah. Okay, so I've realized I have to do this. I have to disconnect it and reconnect it. Power down, power up completely. Yeah, there you go. Gyro. Yeah, so the gyro is whatever. I don't know why it's not showing temps. Let's see why it's not showing temps. Oh, it is showing temps. Yeah, here's the temp. But I would like a new line somewhere there. Cool, it's showing the temperatures here. Okay, fine. So the other thing we can do is now we can get rid of all the other extra stuff. We don't really want we don't really need the accelerometer stuff. We can remove that. We can remove that. We can remove that, and I don't need that. I don't need that. Print S as and now string. This is a now string. G. Yeah, okay, cool. So whatever. Now string is like some sort of like time or whatever. I don't really need that. I don't need that. Just get the temperature. Okay. Okay. No, what? Why is now string it is used. It is used here. Yeah, where this. Yeah, sure. Remove all those warnings. Yeah, there's a temperature sensor. Cool. So let's actually go and implement that power saving thing now. That power saving thing now that we wanted to do. 50 hours later. 50 hours later. 50 hours later. 1 eternity later. Let's add that. One eternity later. Cool. Actually, so this is quite simple, to be honest. It's really simple. I'm not even gonna make a second stream on this one. So let's actually just go out. Let's go to drivers. Let's go to sensor, and then let's go into I think MPU6050 if it's here. MPU6050 probably. MPU inversions. Okay, cool. So let me just go. Let me go. I've been everywhere. MPU6050, MPU6050. That's fine. That's fine. TDK. Okay. TDK. Okay. Yeah, MPU6050 is in here, and then we go here MPU6050C, and basically the thing that we want to do in order to implement so device runtime power management, which is what we're doing now. Device runtime power management. This has been crazy. This has been a crazy stream. Zephyr power management. It's really, you'll see, it's really simple. It's really simple. So in order for us to do device power management, which is what we want, which is the one that is recommended, the preferred one, device power management is a feature which prevents mechanisms. So we read that. So the one we want to introduce is device power management states. So device model with device power management support. Basically, all we need to do is implement this part. So when we're doing all of this, dummy device dt init. Okay, cool. Okay, cool. So we need to first of all implement power management callbacks, which we'll just add. Like they're not even that hard. It's this ones. We can just put them in. Copy. And we don't even need to do anything right now. We can just add them in right now at the bottom. I like putting them at the bottom. This is gonna be painful because we have to mod all of this because we are not going to end up using dt for inst. Sensor dt define. Sensor define. I don't want to do sensor define. I want to do sensor dt inst dinit. I'm not dying. Sensor dt. Sensor device. So PM device. What is a PM device? PM base, blah blah. So I need to make a PM device. Basically, I need to add a PM device and add it into here. This null here. The third item is usually the PM power management device. The third item here. So what I need to do is probably make a power device. It's fine. I'm just gonna finish this. So the thing I need to do is make a power device and hand it over into the device itself. So I'll show you how we do that. I've done this before. It's just time consuming. So this PM action, you see this PM action, you need to hand that PM action into see this PM dt is defined, and then yeah yeah. You see here, we need to pass that PM device. Okay, cool. So we just, all we need to do is PM action. Yeah, we need to just define this. This is okay. We're gonna take a break after this, but it's fine. So in here, I usually like to do it after init or even before init, so that's fine. I don't know. So here we're gonna have MPU6050. What do they call this thing? MPU6050. Okay. MPU6050 PM action. So MPU6050, MPU6050, 6050 PM action. Okay, cool. And then in here, we just, instead of this, what we're gonna do before we call all of those, before we call any of those ones, what we want to do here is just go log inf suspend action invoked. Okay, and then log inf action resume action invoked. Okay, log inf turn off action invoked. All of this are like actions that we have to actually implement ourselves, but for now, like this is the basis of it. It's just turn on action invoked. Okay, so this actually makes it, we will have to implement functions for those, all those logs, but for now we don't have to. Yeah, I mean, for now we, like, if you go through the device tree through Zephyr, you'll find that a lot of drivers have this, but this is not what we're going to submit as our thing. So, and then come in here. Before we do this sensitivity is defined, I think what I remember is this has to be in the new lines, no? This has to be in the new line. So there should be. Where's my new lines? Where's my new lines? I can do it before. I don't know. It doesn't have to be in here. Okay. Define. Define PM device. I don't even know if we have to. We need dt inst define. Okay, and then we just need to do inst here, and MPU PM. Okay, that's it. That really is it. And then in here we come to this null and we say PM device dt inst get. PM device dt inst get. I'll label it n because I just did O. No, I will label it n just to make sure it's the correct one. Or maybe I just should say inst, just be consistent and be like inst I can always just put that on the next line as well. So there it is. So this should actually just build right now. And I'm gonna make a dirty commit and push it up, and then we'll come back and we'll clean this later. Let's see. Yeah, those ones they're not defined, so let's actually get them to build fine. And I suspect it's because I need to import some stuff up here. PM device. Okay. Okay, cool. Let's see if they work out. And this should actually just make it. So this is how we add the power management to our device, basically. This looks like it might actually build. Cool. MPU PM action is unused. Is unused. So later we'll come back and we'll actually implement all of that. And driver PM action. So why come on. That is used. That is exactly used. Because we have it here. MPU6050 PM action, okay. It is there. I don't think it's unused as much. PM. Let's see. Aha, we need to call it. We should be calling it from the other callbacks. It is fine. Okay, cool. So we do need to do that. Okay, cool. So in it, the last call of init should be to initialize that. Okay. MPU6050 PM action. Okay, cool. So this is fine. This is okay. So init does actually use it now. And this should now give us a nicely building up. Okay, so that's that. I don't like the warning, but we can live with the warning for now. Okay, let's stop there. Let's stop there. It's been 4 hours. Surely it's been long enough. Let's stop there. Let's leave it at that. I'm gonna close this code and I'm gonna put it on a branch, some branch. Git okay. Git status, git add samples, hello world. Okay, cool. Git checkout dash b dati MPU dati MPU6050 PM. Git add samples basic samples hello world. Git add drivers. Git commit dash m basic PM work for 6050. Okay, git push gouges. Perfect. Bartlomiej, you can find the code here. So there is a code. I'm gonna put it in the Discord now. So I'm gonna stop the code here and I'm gonna come back tomorrow or later and finish this all completely, because now we just look, it's not that hard. It really isn't that hard. It didn't have to be as hard as it is. I made it harder by explaining what I was doing. I don't know if I should keep doing that, but I like explaining what I was doing. So if you go through this document here, this power device, all these functions, it just describes, it's just all of these things of like turn off the pins, turn on the pins, turn off the pins, turn on the pins, turn off the pins, turn on the pins. And you can implement all of those callbacks. And once you've implemented all of those callbacks, it's as simple as doing, what is it called? Okay, config PM device. That's it. And then Zephyr handles the rest for me, basically. I'll go on with this tomorrow probably. We'll see. Yeah, sure. Thank you so much for coming. Thank you so much for being here with my frustration. I'm gonna see if I can get NRF SDK going. I'm pretty upset with them that I cannot just use the thing at 3.3v. Just I can't fathom that. Anyways, thank you so much for showing up today. That was a long stream. I like doing them. Thank you so much for bearing with me, and see you later. Thank you so much. Cheers, people. Cheers, Bartlomiej. That was especially for you. Cheers.